let's do this thing. We are going to find the critical numbers. Those are the x values. We are also going to determine if we have intervals of increase, decrease, or constancy. We're also going to state if each critical number corresponds to a relative max, minimum, or neither. It's going to be fun. Let's jump right in. So we have this function, x squared minus 14x plus 2. Let's just go ahead and be really realistic about this. You know that this is a parabola that opens upward. Already, you know this much. Decrease, increase. We just don't know where that is. We don't know that x value. So we're going to use the derivative. So here we go. The derivative is 2x minus 14, okay? And that's equal to 0 because critical numbers occur where the derivative equals 0 or where the derivative doesn't exist. But this derivative is going to exist everywhere. It's a line. It's good, all right? So we solve, we get 7. So we automatically have identified a critical number. So yes, mission accomplished. We have done the first thing they want us to do. So we have a critical number. Let's just abbreviate. We'll call it that. So let's determine the intervals of increase, decrease, or whether or not it's constant. Now, again, we already know that this parabola does this, so we're going to have decrease then increase, and we know it's going to transition at 7. So let's do a little number line trick. I like to call this sign analysis. I'm not the one that came up with that, so I can't be like, I like to call it sign analysis. So here's what we're going to do. This is going to be wordy, but bear with me. A function is increasing when its derivative is positive. A function is decreasing when its derivative is negative. And we've already discussed that at the beginning of this lesson. So what I'm going to do is pick any number between negative infinity and 7, which is in that interval, and plug it into the derivative. When I plug it into the derivative, I don't care what I get. I care about the sign of what I get. So let's plug something in. Random number between negative infinity and 7. Okay, not so random. 0. 0 is going to be an obvious one. If I plugged a 7 into the derivative, I would have a noisy marker. If I plugged a 0 into the derivative, I would get negative 14. Okay, so negative 14. I wrote way too much here, way more than I normally write. What I am going to write instead is this. F prime is negative. That's all I care about. This was a thought process. This is what I care about. Automatically, I can go ahead and start answering the third part, which I will do right now in red. So this, the second part. The function is decreasing on the interval from negative infinity to 7. All right, let's move on. We're going to plug in a number in this interval. 8, 9, 10, a million. Who cares? Let's use 8. So if I plugged in an 8, I will plug it into the derivative, f prime of 8. It's going to give me 16 minus 14. That's going to give me 2. That is fine. That happens in your head. I got it. You got it. We're happy. There you go. We are going to instead just write this. This is the big idea. The derivative is positive on this interval. Therefore, the function is increasing on that interval. Increasing on the interval from 7 to infinity. Yay! All right, great. Let's keep moving. State if each critical number corresponds to a relative maximum, minimum, or neither. Well, you know what this parabola looks like. You know it does this. So that must be a minimum. But let's articulate this knowing more than just a little bit of algebra skills, okay? Other than the fact that we know what this thing looks like, let's walk over here and use some logic, okay? Walking slowly. The derivative is negative, then the derivative is positive, okay? That transition happens at x equals 7. Let me word this differently. Excuse me, I had to clear my throat for it. It's important. The function is decreasing, then the function is increasing. If my function is decreasing, then increasing, then this point down here must be down here. It must be a minimum because the function transitions from decreasing to increasing because the derivative transitions from negative to positive. All right? You can determine highs and lows using this. It's great. So this one's fairly obvious. It's a parabola. We're just sticking our toe in the pool. But let's keep writing. State if each critical number corresponds to a relative maximum or minimum or neither. I will write this one in black. And here we go. X equals 7 corresponds to a relative, actually it's the absolute minimum, but relative minimums can be absolute. Absolutes are relative, okay? Let me rephrase that. That's the lowest point on the entire graph. It's also the lowest point in its little region. It's the absolute minimum. It's also a relative minimum. Anyway, x equals 7 corresponds to a relative minimum because we're learning to articulate things in a way that they will grade it on the free response section. X equals 7 corresponds to a relative minimum because f prime changes from negative to positive. There we go. At that point, f prime changes from negative to positive, which means the function changes from decreasing to increasing. Okay, let's do the next one. The next one is cubic, so it's not going to be, it's going to be, whoop. Before I go to the next one though, can I show you something cool that you've seen, but you didn't realize you had seen? Okay, next problem is cubic. Let's hold that thought. Let's pretend like, get ready, it's going to be so much fun. Let's pretend like instead the problem was almost exactly like this one, but it wasn't so specific. Let's suppose that the problem that we were given was just a generic standard form ABC of a quadratic. Okay? Watch this. This is so cool because you've learned this before and didn't realize where it came from. It took me a while. When I first saw it, I was like, that's where it comes from. Let's take the derivative. Okay, a times 2 is 2a. X to the first. The derivative of bx would be b. The derivative of c goes away. Let's set this equal to 0. Okay, solve it for x. We will subtract b. Do you know where this is going? It's so much fun. Okay, solve. Let's divide by 2a. X equals negative b over 2a. We have, seen that before? That is the x coordinate of the vertex of a parabola. And that's where it comes from. Using the derivative in just a standard form, ax squared plus bx plus c, 2ax plus b, you solve it and you get this. That's where it comes from. Okay, next problem. Aren't you glad you know that now? Your life is fulfilled at this point. You could just turn the video off and just say, this is great. X cubed plus 3 halves x squared. So x cubed plus 3 over 2x squared. All right, writing with a squeaky marker. F prime is 3x squared plus 3 halves times 2 would be 3x. We're going to set that equal to 0 and solve it. So equal to 0 and solve it. We can factor out a 3x, so 3x and then x plus 1 equal to 0. So 3x equals 0. That squeaky marker is right next to the microphone. Sorry about that. X plus 1 equals 0. So we have critical numbers at x equals 0 and x equals negative 1. Let's do sign analysis. Sign analysis is where we draw a number line, mark down the critical numbers in this case, next lesson or next couple lessons. It'll turn into what we call points of inflection. And in this case, we're going to just deal with critical numbers. So we have identified critical numbers. Let's grab a different color marker. Walk over here, stand in front of the work so you can't see it. Negative 1, 0. And we're going to plug numbers into the derivative. When I plug numbers into the derivative, I do not care what I get. I only care about the sign of what I get. Do I get positives? Function's increasing. Do I get negatives? Function's decreasing. Do I get 0? Well, I shouldn't get 0 because then we will have hit those points. So in the directions where it says determine intervals of increase, decrease, or constancy, with these polynomials, we're not going to have anything that's constant. So at the top of the page, you see this little thing that goes up and then down and then plateaus. That's not going to happen on a polynomial. We both know that. Okay. Let's plug a number into the derivative from each interval. So here goes. Pick a number between negative infinity and negative 1. Negative 2 can pop in your head. If you plug a negative 2 into the derivative, pause right there. I used to do that. And I plug a negative 2 here and here. Don't. Go, if possible, go to factored form. Because if this was calculator inactive, then we would plug it in here. I'm going to plug a negative 2 in here, and you have to follow what's happening in my head. If you plug a negative 2 here and here, you will have negative 2 times 3. That's negative. We have a negative times a negative 2 plus 1. That's negative. Negative times a negative is going to give me a positive. I do not care what the number is. I care that it is positive. So the derivative is positive here. Did not show any work. I apologize for that. But again, here's what's going on. Plug in a negative 2 here, you'll get a negative. Plug in a negative 2 here, you'll get a negative. Negative times negative gives me a positive. Okay, let's plug in the, we have more limited options here if we're going to go for easy numbers. So negative 1/2. We plug in a negative 1/2. If you plugged in a negative 1/2 into this factor, you would have a negative. You plug a negative 1/2 into this factor, you get a positive. Negative times a positive is a negative. Okay, let's do it again. Plug in a positive and a positive. This one's going to be a little more obvious. Positive goes here, gets a positive. Positive goes here, gets a positive. You're going to have a positive. Okay, let's keep writing. Determine intervals of increase, decrease, or constancy. I'll put this answer over here. The function is increasing on the interval from negative infinity to negative 1, and we'll keep going from 0 to infinity, and decreasing from negative 1 to 0. Okay? Let's also determine if this x value corresponds to a maximum or a minimum. Okay, if it corresponds to a maximum, then the function will be increasing, then decreasing. That is what happens. The function increases, then decreases. Therefore, at x equals negative 1, we have a maximum. The function goes up, then the function goes down. This has to be a maximum. Similarly, the function goes down, then the function comes up. That has to be a minimum. Let's write that down. We have a relative max at x equals negative 1. And if I'm going to write all my reasoning out, then I would say, and I will write it in a second, but I would say the function transitions, the derivative changes from positive to negative. Relative max at x equals negative 1 because the derivative changes from positive, my head might be in the way, positive to negative, and then we're going to have a minimum here. So relative minimum at x equals 0 because the derivative changes. It's good for us to articulate what we know. Good practice for free response. From negative to positive. There we go. We've worked through a couple examples. We'll do a few more in some other videos.